I want to look at this one as a tangent line rather than the linearization formula. The linearization formula is just a formula that tells you what the tangent line is. So let's go back to what we were doing in chapter 3 and just write the equation of the tangent line. So I'm not going to draw a picture again. You guys know what the square root function looks like. You know what tangent lines look like, right? So what do I want to do here? I'm going to use the same function. F of x is the square root of x. And then we know that the derivative of f of x is going to be 1 over 2 square root of x. So what am I going to do here to write the tangent line? And let me ask this first. At what point do I want to write the tangent line?
4.
Yeah, why 4?
It's close to 5.
It's close to 5, exactly. So we're going to write the equation of the tangent line at 4. So we know that the point 4, 2 is on the line. So what's the equation going to look like? What do I need to know? I need two things. I need a point, which I have, and the slope. How do I find the slope?
Put 4 in for x.
Plug 4 in for x where?
In the derivative.
Into the derivative, exactly. So the slope at 4 is going to be the derivative at 4, which is going to be 1/4. Good. Okay, so then the tangent line, equation of the tangent line is going to be
Y minus 2 equals 1/4 x minus 4.
Now, you guys probably notice here that if I just added 2 to both sides of this equation, then it's the linearization formula. If it was y equals 2 plus 1/4 times x minus 1, that's the linearization formula for the square root function at 4. What?
X minus 4.
I don't know why it's 1, because that's what I wrote. X minus 4, sorry. Okay, so then how do we figure out what the value of the tangent line is going to be at 5? Plug 5 in for x, right? So we're going to have y minus 2. Let's go ahead and add 2 to both sides. So it's going to be 2 plus 1/4 times 1, which is 2 plus 1/4 is 2.25, which tells us then that the square root of 5 is approximately equal to 2.25. Now, I don't want you guys to get the idea that the square root of anything is going to be approximately equal to something 0.25. It just happened that way in both examples. How accurate is that?
Less than before.
Not as accurate, right? Okay, so how accurate is it? What is
2.236?
2.2361 and so on? Okay, you're right, it's not as accurate. Now, I think that's interesting because 5 is closer to 4 than 150 was to 144, right? So why and let me put the graph up here, and I'm going to just go back to our last slide here. Why is it that that we get a more accurate answer in this region here? Sorry. Why do we get a more accurate answer in this region here than we get in this region here? No.
Second derivative is closer to 0?
Yes. Good. The second derivative is closer to 0 here, right? Why does that matter?
Because that's the change of slope for the tangent line.
Okay, good. So the second derivative tells us how fast the slope is changing, right? So here, the second derivative is bigger. It's actually going to be negative because it's concave down, right? So the second derivative is negative, but it's curving more. And we measure curvature by taking the second derivative. So it's curving more here. So even though we were closer to the point here, since it's curving more, this part of the curve is less like a line than this part. So the closer the second derivative is to 0, the more like a line the curve is. Does that make sense? So when the second derivative is close to 0, then we're going to get an accurate approximation. if the second derivative is not close to 0, then we have to get really close to the point to get an accurate approximation. Does that make sense? So what we're going to do when we start measuring the error is we're going to use the value of the second derivative to figure out how much error we might have.